Let's evaluate the contour integral of x over y ds, where the curve C is parameterized by x equals t cubed over 3, y equals t to the 4th over 4, and t is bound between 1 and 2. So first, whenever we transform an integral, remember we need to know the limits of integration, maybe how to parameterize the integrand, and our differential element ds. Okay. So our limits of integration are actually given in t by this statement: 1 is less than or equal to t is less than or equal to 2. So I know that my integral is bound between 1 and 2 in t space. Now x and y, my x is also given to us as t cubed over 3 divided by y, which is t to the 4th over 4. So that takes care of the limits and the integrand. But what about the ds? Okay, so for ds, I'll take care of that on the side. I'll write ds as the root of dx dt, which I write as x dot, say squared, plus dy dt, which I write as y dot squared dt. This just comes from Cal 2. If we were to take a curve and find some infinitesimal piece of it to extract out the total length of a curve. All right, so this would be that infinitesimal piece. So if we know that x is t cubed over 3, then x dot, or dx dt, for t cubed over 3 is going to be 3t squared over 3, which is just t squared. Our y dot, which is dy by dt, so we have a t to the 4th over 4, which is going to give us 4t cubed over 4. So you can see how perfectly engineered these problems are to give us a t cubed. And now our ds is just going to be the root of x dot squared, t squared squared, plus y dot, or t cubed squared dt. And we can simplify this a bit. Let's see, I get the root of, I raise a power to a power, I multiply the exponents. So I get t to the 4th plus t to the 6th dt, or the root, if I factor out a, let's say t to the 4th, I'm left with 1 plus t squared dt, or the root of t to the 4th should give me a t squared root 1 plus t squared dt. Okay, and that's going to be my ds, which I can now bring back here for my differential area element. I mean, my differential length element, ds, as t squared root 1 plus t squared dt. And so now we've taken this contour integral, which was written in terms of x and y, and a ds, and expressed everything in terms of t. Again, the limits, the integrand, and our differential length element ds along the curve. But we have some simplification to do. So here I'll get a what? A 4/3 to come outside the integral. Remember, constants can go in and out of linear operators. I'm still integrating from 1 to 2. I have a t cubed over t to the 4th, which is 1 over t times t squared, which leaves me with just a t in the numerator, times 1 plus t squared dt. All right, so that simplifies pretty quickly. Now to integrate this, we may want to use a u substitution where we use some other function. In this case, I'll say let u equal to the 1 plus t squared. And then we transform again the rest of the integral all in terms of u. So if u is 1 plus t squared, then my du by dt is just 2t. But see, I have a t dt that I can pull out. So I can write this as what? Du over 2, or a half du, to extract the t dt. So that'll take care of the integrand, and really all I have in my differential time element, I just have to take care of my limits of integration and put those in u space. Well, here I have a transformation function. So if u is 1 plus t squared, then when t is 1, u is 1 plus 1 squared, or 2. So u at the lower limit is 2. U at the upper limit is going to be 2 squared, which is 4 plus 1, or 5. So my integral in u space, see if I could write this and not interfere with that, should give me the 4/3. I have a 1/2 that's going to come from the t dt. My integral goes from 2 to 5. And my t dt is just going to be the 1/2 du. So 1/2, I have a du. And this is going to be u to the 1/2 power du. 4/2 just leaves me with a 2. So I have 2/3. And if I integrate u to the 1/2, remember my power rule, I add 1 to the 1/2, that'll give me u to the 3/2 divided by 3/2. So I get u to the 3/2 divided by 3/2, just same as multiplying by 2/3. Evaluate it from u equals 2 to u equals 5. So to simplify this, I get 2/3 times another 2/3, and u to the 3/2 evaluated at the upper limit gives me 5 to the 3/2 minus 2 to the 3/2, or 4/9 of 5 to the 3/2 minus 2 to the 3/2. Thank you.